Helium is 1s2, and this is completely filled shell. 1s shell is completely filled. What about this neon, argon, krypton? What is the general configuration for this family? This part of the family, general configuration. And how many electrons are these? Ns2 and p6. How many electrons are these? Count the total. 6 plus 2, 8. So this is a magic number. Shell is closed. And this is the outermost shell with 8 electrons. In every, if you pick up any element, this is the outermost shell. And with 8 electrons, which is called as octet. But if you look at the elements of the second period, the outermost shell is 2s, 2p, 2s, 2p. Do we have any 2d orbitals here? No, there is no 2d orbitals. So in 2s and 2p maximum, how many electrons you can have? 8. So these are the elements: carbon, nitrogen, oxygen, fluorine. They are always with 8. They cannot have more than 8 because they don't have any empty orbitals to accommodate extra electron. So these are always with accurate 8. They never exceed the 8. Even boron, they never exceed the 8. Beryllium, boron never exceed the 8. Right? But if I go to the next family, next period number, I'm audible? Okay. If I go to period number 3, if you see, the outermost shell is 3s, 3p, and there is empty 3d. So it can have electrons in the p as well as in the d. Like for example, let's take chlorine. And chlorine has total valence electrons. Yes, 7. This is 3s2, 3p, 5. Total valence electrons are 7. Now, only one electron is available. I think this is what I discussed in the last class. Only one electron is available for sharing. So chlorine can make one bond like this, where it is following exactly 8 rule. If it shares one more, it's exactly 8. But electron can jump from here to here. Now, how many bonds chlorine can make? 3, like this. And how many electrons chlorine has? These are the 2 lone pairs. Now, how many electrons chlorine has around it? Every bond is a pair of electrons. So how many total? Check, check, check. All pairs. Anaya? Yes, 10. Is 10 8? No, it's more than 8. But chlorine can make these kind of bonds. There is a molecule, ClF3, where chlorine is making 3 bonds with fluorine. This is expanded octet, more than 8. You can jump one more electron from here. Jump one more electron from here, and it will come here. 10. How many unpaired electrons? How many unpaired electrons? 5 unpaired electron. 5 unpaired electron means chlorine can make how many bonds? 5 bonds. With how many lone pairs? Lone pairs? One lone pair. Amodita, you are getting it? And total, how many total electrons here? This is more than 8. And we do have molecules of chlorine making 5 bonds with 5 fluorine, like this. These are there. Okay, so this is the meaning of expanded octet. Now answer my question. For expanded octet, what is needed? Elements can show expanded octet if they have empty d orbitals. And from where we get the empty d orbitals? We start getting empty d orbitals after second period. In third period, these elements, they have empty 3D, which is not filled. 3D is filled here, 3D is here. For the fourth period elements, empty 4D, like this. The presence of these empty orbitals is the reason that elements have expanded octet. This one has, these are empty. I'm talking about empty. Vacant. Empty means vacant, where the electrons can be excited. Yes, ma'am. Amodita is asking that why not in second period? Second period elements are exactly with 8. The reason? Because we don't have any vacant 2D. If you remember, 2D does not exist. We did the quantum numbers. When n equals to 2, second period, n equals to 2, the values of L are 0 to n minus 1, which is 0 and 1. 0 is 2s, 1 is 2p. Where is 2d? There is no 2d. Okay, this is very important question. That elements of second period cannot have expanded octet, and elements of other than second period means after second period, third period and onwards, they can have expanded octet because of the presence of vacant d orbitals. Okay, now let's come to the another rule. So we have seen two rules. One is exactly 8 and other one is more than 8. Now there are elements which are going to have less than 8 in their molecules. Now let's have a look at this boron. What's the configuration of boron? 1s2, 2s2, 2p, 1. This is 1s, this is 2s, this is 2p, 1. So in this is the ground state. How many electrons are available for sharing? How many? If it shares 1, it will get 1, but that's not going to complete the octet of this 2s and 2p. So what is the excited state? Electron jumps from here to here. Now, how many electrons are available for sharing? So how many bonds boron can make? Only 3, because it's giving 3 for sharing. So it will make only 3 bonds, not more than 3. But when it's making 3 bonds, what are the total number of electrons around boron? 6. Is 6 octet? 6 is not octet. But still, these molecules are there. BH3, BF3, all these are there. ELH3, this aluminum, same family, same valence electrons, same kind of situation. But yes, it can also have expanded octet. Okay, how many unpaired are here? Who is going to help Amodita? How many unpaired here? And for sharing, If boron is sharing, one electron will come from boron. These are the three electrons, unpaired electrons, which are coming from boron. And the other electron is coming from hydrogen. The other elements, like fluorine, in the molecule, in a bond, from here. It excited from here to here. This is the ground state and excited state. You missed this session, Amodita. That's why you're confused. This is the ground state of the boron. And now ground state is giving you only one unpaired electron, one sharing, but one is not sufficient. So electron jumps from 2s to 2p. Now you have more unpaired. More unpaired means more bonding, more stability. Bonding is attraction. So elements, they excite their electrons in the vacant orbitals. These are the vacant. This is 2p is vacant, not d here. Okay, this p is vacant. So that's why electrons are getting excited in p only. So it cannot exceed octane, but here it can have less than 8. Okay, so whatever number of electrons you will give for sharing, you will get exactly same number of electrons. Beryllium. Let's discuss the ground state of beryllium. 1s2, 2s2, and there is 2p, which is vacant. This is the outermost shell. So electron jumps, like these are shared with the shared electron. This case is only with beryllium. Rest all are metals, very high. This is also metal, but with some elements is making covalent bonds. It can make covalent molecules. One electron jumps from here to here. Now, how many electrons are available for sharing? 2. How many bonds beryllium can make? 2. But with 2, how many electrons are there around beryllium? 4. But 4 is not an octet. But we do have molecules like BeF2 is there. BeH2 is there. These molecules are there. Be, that's ionic. So these are the molecules which are there with beryllium. Beryllium is metallic, but with the few elements, it can make covalent molecules because of its very small size. Small size means more non-metallic character. Okay, so that's the story about the more than 8, less than 8, and exactly 8. So do you think carbon can have more than 8? In its Lewis dot structure, carbon, nitrogen, oxygen, fluorine? No. What is the reason? Absence of empty or vacant d orbitals, because there is no 2d. We don't have any 2d, right? Okay. So now I'm taking you on the next topic, that is formal charges. Before starting the Lewis dot structure, in the unit 2, I'm teaching you slightly not in a regular sequence the way it is written there on the website. I'm teaching you now Lewis dot structures, VSEPR, and I'll come back to the other topics once we are done with this. So when you're doing the quizzes, you have to select the quiz. The topic which we have done, do that quiz. Okay, so what's the meaning of formal charge? Anaya, I have to open it. Sorry, I didn't open it. Mayank told me just now that quizzes are not open. I can open it right away. 1 second. You can see after the class, you can see the quizzes there. Unit 2, right? Okay, it's open. And there are some videos of last year which I'm going to remove, but otherwise quizzes, everything is open. Okay, so let's do the formal charts. So what's the meaning of the formal charts? This is very important topic for chemistry. Formal charges. I'm teaching this formal charges for organic chemistry student, MCAT student. So this is a topic which is without this you cannot learn chemistry properly. So and it's very easy topic. You have to understand it. Now you remember that boron. I was making the electron configuration in the excited state as 1s2, 2s1, 2p2. Is it okay? One electron here, two electrons here. This is the excited state. And these are two. During chemical bonding, boron is going to share its valence electrons. So how many valence electrons boron has? 3. With 3 valence electrons, how many electrons boron is going to use in its Lewis dot structure? It's going to use 3. If it uses more than 3 or less than 3, then it acquires a formal charge. But if it is going to use exactly 3, then formal charge will be 0. So formal charge basically, there is a definition here. So formal charge basically, the basic definition is this one. How many valence electron that element is formal charge first thing is per element. It's not on the molecule, it is on the element. It's the valence electron of the element minus how many electrons it has used in making the Lewis dot structure. In making bonds around it, in making lone pairs around it. So that is the formal charge. If it is using exactly its valence electrons, then formal charge is 0. If it is using more than, then negative. If it is using less, then positive. Let's see an example. Like boron, you can see in your molecules like this. So in every bond, boron is using how many electrons? A chemical bond. Every bond, 1. In every bond, boron is using 1 for sharing, right? So it means the number of bonds around boron is the number of electrons used by boron. So what's the formal charge? Is there any lone pair on the boron? No. What's the formal charge here? 0. But if I give you something like this, you can see like this also, BH4 minus, BH4 minus. Can you check the formal charge here? For every bond, boron is using 1 electron, but boron is giving only 3. So it means it has gained 1 extra from somewhere else. So see, BH4 minus. So that's how you have to understand the formal charge. Ready for some examples? So when we are calculating the formal charges, you have to see how many valence electron that element is giving and how it is using these electrons. So there are different equations in different books. This is also very popular, but I think you should go with this one and this one. The electrons used are in the form of bonds. Just count the bonds. Like I was counting around boron. Like for example, if I give you NH3, can you tell me how many valence electrons nitrogen has? Valence electrons, nitrogen, 5. How many it is using in bonds? So the number of bonds are the number of electrons used by nitrogen for bonding. And how many are there as lone pair? There is one lone pair Every lone pair means 2. That's why the word 2 is, sorry, not this one, 2 is here. 2 times 1. What's the formal charge on nitrogen here? 0, 0, 0, right, Amadita? Okay, now let's see if I give you nitrogen in this manner with 4 bonds. So how many valence electrons? 4. How many it is using as bonds? Count the bonds. So number of bonds is the number of electrons used for bonding. 4. Any lone pair? So plus 1, right? Okay, giving you more examples. Check this. Check the formal charge on this oxygen when it's making a single bond with 3 lone pairs. What's the formal charge? You can use any equation. You can use this one. I think leave this one, or you can use this one. Your teacher may give you another one also, but I think these are better. Mhm. Yes, -1. And if I give you oxygen like this, if I give you oxygen like this, if I give you oxygen like this, okay, those who have not answered, you can put the sequence like this. Okay, Mink. Amadita, your answers? You can use this equation, right? This is faster. 6 -1 minus 3 times 2 is -1. In this case, 6 -2 minus 2 times 2, 0. In this case, same situation. 6 -2 minus 2 times 2, 0. In this case, yeah, here, how many valence electrons? 6. How many electrons are used in bonding? How many bonds? 3. How many electrons are there as lone pairs on oxygen? On oxygen is 2 times 1. So what's the formal charge? +1. This is +1. Or you can do like this. You count the electrons. Oxygen has 6 valence electrons. So I'm showing you oxygen electrons here. 1, 2, 3, 4, 5. So out of 6, it has used only 5. So formal charge is +1. Check here. Oxygen electrons 1, 2, 3, 4, 5, 6. So out of 6, we have used 6. So that's why formal charge is 0. And when the formal charge is 0, that's a happy situation for the element. So this is how oxygen can be seen. Here, any element is there. It can be any element. That I will teach you that why we are using only 5. Like for example, this is water. You know that. I'm answering the question asked by Amodita. This is water. Now H plus approaches. In H plus, is there any electron, Amodita? H plus, how many electrons? Find the number of electrons in H plus. 0. Now it's approaching, it's very reactive. It's acidic proton, very, very reactive. Oxygen has lone pairs. Now oxygen is giving both the electrons for sharing. and is making a bond with this H plus, like this. Now the same hydrogen H plus, the green one, I'm making it with the green one, is here. Now there is no charge, but oxygen is left with one lone pair. So what oxygen has done? It has given its lone pair, this lone pair over here. These two electrons have come from oxygen because hydrogen was without electron. So this is a sharing, but what kind of sharing? Electrons have come from oxygen only. It's not any, none of the electron has come from the other element. So this kind of bond where only one element is giving electrons for sharing is called as coordinate covalent bond. Coordinate is different. Covalent bond. One electron was supposed to come from this hydrogen. Like here in the with the other hydrogen, one electron is from oxygen and one electron is from hydrogen. But in this hydrogen, the one which has come without electron density, both the electrons have come from oxygen. Can you check the formal charge here? Check the formal charge on this, in this molecule. Sorry, in this one. I'm making it again. Formal charge on the oxygen is +1 because it's giving its electron to hydrogen. Now this electron is, it appears that hydrogen has given, though it has not given. Electrons are given by oxygen. So oxygen is using its electrons, the one which are here, which you can say has come from oxygen, only 5. But actually all the 6 electrons are used, but now this electron appears to be from hydrogen. Okay, so we have understood these formal charges. Few more practice. So whenever element is in zero formal charge, means it is using its valence electrons exactly in the same number, not gaining more or not giving electrons to somebody else like oxygen was doing, then the element is in happy form. Happy means stable, happy, and it's there will be no formal charge on that element. Let's see. I'm going to show you some examples and you're going to answer the formal charges. Number 1, number 2, yes. Which one for the first one? Okay, you're saying 1, 0. Yeah. Okay. All are 0. So you can see chlorine like this. Which one is exactly with 8? Which one is exactly with 8? The first one. The rest all are with expanded octet. The rest all are with expanded octet. You can see here how many electrons. So why is it so? Because chlorine can have expanded octet. Now answer my question. Do you think fluorine can do so? Do you think fluorine can have these kind of situations? No. Fluorine can have only option 1. Only option 1. So here comes a very important statement that fluorine never makes a double bond. If you see the configuration of fluorine, it is 1s2, 2s2, 2p5. It needs only one more electron. So fluorine never makes a double bond. So please write on this, print it in your in your memory. Fluorine and hydrogen, even hydrogen, it can take only one electron, not more than one. So fluorine never makes a double bond. Hydrogen, what do you think hydrogen? 1s1. After taking one electron, its shell is closed. Hydrogen also never makes more than one bond. So fluorine and hydrogen, these are two unique elements which you have to remember that they are never going to make a double bond or triple bond. They are always going to make one single bond. Is it okay? So we are starting with how to write Lewis dot structure after understanding the formal chassis. So we are going to do plenty of examples. Be ready with your paper pen because you need to write down everything. We'll follow certain rules. See, children, rules, they help you in doing the things in the right manner. And when we say rules, then it means you have to follow the sequence also. If you break the sequence, you will end up with some wrong structure. And when we are making the Lewis dot structure, we need to know the understanding of the electronegativity and expanded octet, formal charges, and valence electrons. We have already mastered that, right? So I think we are comfortable. As we discuss the rules, you will find them very easy. So the very first rule is you have to select the central atom, which is least electronegative. I'm picking up an element SO4 2 minus. So which one is the less electronegative element here? Sulfur. Okay. Now rule number 1 says select sulfur. So I have selected sulfur. Now rule number 2 says that you make a skeleton of these 4 oxygen with single bonds. These 4 oxygen with single bonds. Like this. The oxygens are going to make at least single bond with sulfur. One bond is minimum needed. Okay, see this line is clear? This red one. Remember, hydrogen and fluorine are never the central atom as they cannot make more than one bond. You remember I was telling you hydrogen cannot make more than one bond. Fluorine cannot make more than one bond. So they can never be the central atom because central atom should be capable of making more than one bond. It should be making more than one bond. So hydrogen and fluorine are never the central atom. This is rule number 1 and rule number 2 is, this is rule number 2. Okay, now I'm taking you on the next rule, rule number 3. In rule number 3, you are going to count the total valence electrons. And if it is an anion, add extra electrons, means extra electrons are there. If it is a cation, then subtract it. Like this is an anion. So count the total valence electrons. So total valence electrons, I will be writing TVE. Sulfur has how many? 6. Oxygen, 4 times 6. And then this 2 minus means plus 2. How much is this total? Can you see that I have added 2 because there is 2 minus? I think 32. Did you add this 2? Meg, this 2 minus. See the rule number 3. Add 1 for each negative. If there are 2 negative, add 2. Subtract 1 for each positive, right? So 32. Okay, now let's go for rule number 3. We have done the valence electrons. Now we know the total valence electrons. Complete the octet of the most electronegative atom. Now, most electronegative atom here is oxygen. Now look at the periodic table. See, right now I'm teaching you rules, but very soon you will see that you within a minute or two you can draw the Lewis dot structure. After understanding the rules, we'll follow very fast things to make the Lewis dot structures. So look at the oxygen. How many unpaired electrons oxygen was holding in its outermost shell? Draw the configuration. How many unpaired? And how many lone pairs? Remember oxygen 1s2, 2s2, 2p4. When you draw this box representation for the outermost shell. So how many bonds maximum oxygen can make? How many? Only two. So and two lone pairs. See this is a lone pair on oxygen. This is a lone pair on oxygen. So put them as lone pairs. Two lone pairs, two bonds, but there is no other element here. So make two bonds. Double bond. Check the formal charge on this oxygen. If you check the formal charge, you can count the valence electrons like this. 1, 2, 3, 4, 5, 6. 6 minus 6, 0. Right? So this oxygen is very happy. Minimum formal charge, 0 formal charge. Can you think about this oxygen, what this oxygen can do? Same thing. This oxygen can also do the same thing. 0 formal charge, 0, 0. What about this oxygen? This oxygen can do the same thing. Now remember, now just pay attention to sulfur also. Check, sulfur can make maximum how many bonds? Anaya. Sulfur, same electron configuration for sulfur, but then it is 3s, right? This is oxygen, sulfur, 1s2, 2s2, 2p6, outermost shell is 3s2, 3p4, but 3d vacant are lying there, so you can excite all the electrons. So how many maximum bonds sulfur can make? 6. But if I make a double bond, don't you think it's more than 6? Now you start paying attention to the central element also. Just check that how many unpaired electrons central element is providing. So it means don't make another double bond. Then complete the octet of this oxygen. For completing the octet, how many lone pairs are needed? 3. Now the octet is done. Now check the formal charge on this oxygen. Check the formal charge. -1. But you have, see, they are saying minimum formal charge, but I cannot make more than 6 bonds on sulfur to make this oxygen happy. As it is, the species has a 2 minus, and these 2 minus will go on 2 oxygens. When there is a negative charge in a polyatomic ion, sulfate, nitrates, carbonates, remember the negative charge is on the oxygen, on very electronegative atom. Same here. Is it clear? There's a formal negative here, formal negative here. Check the formal charge on sulfur. Check the formal charge on sulfur. 0. Check total number of electrons used. You have to check that whether we have used all 32. So that you can check like this. How many are here in this circle? 8. You ensured 8 for oxygen, right? How many are here? 8. This circle, this including the bond, 8. 8. All 32 are used. Is sulfur with 8 or more than 8? Sulfur is using more than 8. Expanded octet. Expanded octet is a very common phenomena in polyatomic ions. Okay, ready for another? So this is how you have to follow the rules. So first you have to see the uh, central at that most electronegative atom, complete the octet. Then you check how many electrons are used, how many are left. If something is left, then put it on the central atom. So I'm going to make you understand rule number 5 now. Let's pick up this example. Ready? Essential. Hmm. Okay. So central element follows rule number 1. Sn is here. Okay. Make skeleton means make single bonds with 3 chlorines. Here chlorine is not the central element. It is on the central element can make more than 1 bond, but other than central element, then you have to check the formal charge. Count total valence electrons. Yeah, total valence electrons. Take care it has a minus. Tin is in carbon family. Chlorine is in halogen family. Tin has 4 valence electrons. Chlorine has 7 valence electrons. So there are 3 chlorines, 3 times. How come you are getting such a small number, Anaya? And then there is a minus. So it means 1 extra. Okay, okay. 26. Okay, now complete the octet of the rule number 4. Complete the octet of the most electronegative atom with minimum formal charge. Yes. Chlorine is the most electronegative atom. And you have seen that how chlorine can make double bonds and all these things. So, but if I put a double bond here, then is this chlorine in a happy situation? Check the formal charge. No. So don't put a double bond here. When, write down this also. When chlorine is not the central atom, not chlorine, all of them. Fluorine, chlorine, bromine, iodine. Fluorine is never the central atom, but chlorine, bromine, iodine can be the central atom. But if they are not central atom, then they are going to behave like fluorine. They will share only 1 electron and they will make only single bond. So this you write down in your notes somewhere. Halogens, they behave like fluorine if they are not the central atom. Like fluorine means 1 single bond. So all these chlorines are going to make 1 single bond to have minimum formal charge like this. Check the formal charges. Chlorine has 7 valence electrons, right? 7. Now 1, 2, 3, 4, 5, 6, 7. 7 minus 7, 0. Okay. Now check how many you have used. You have used 24. How many are left? Where these 2 electrons will go? Now these are 0, 0. Who is holding the formal negative? This negative? Check tin. How many valence electrons tin has given? Only 4. How many it is using? Let's check that. How many it is using? 1, 2, 3, 4, 5. 4 minus 5? Minus 1. Show this formal charge here. So tin has a minus 1 formal charge here. So is this rule clear? Check the total electrons used, and if something is left, place it on the central atom. Ready for another? These are the important rules. Let me see. Yeah, these are the only rules. Now we are going to practice. Okay. NO3 minus. Nitrogen is here. Do you think nitrogen can have expanded octet? Maximum how many bonds nitrogen can make? Oh no, Anaya, no, no. Only 4. If it is making 5, I know its valence electrons are 5. But if it is making 5 bonds, then electrons will be 10. So Amodita is right. Maximum it can make 4 bonds only, not more than 4. Okay? Because making 5 bonds means 10 electrons. P can make 5 bonds. P, arsenic, all these can make 5 bonds, but not nitrogen. So follow the rules. Central element, skeleton, total valence electrons. I'm following the rules the way I've written. Yes, who is going to give me total valence electrons? There is a 1 minus there. 1 minus, Mayank. You're not adding this minus? 24. Okay, complete the octet of the most electronegative element with minimum formal charge. Most electronegative is oxygen. If you remember, oxygen is very happy to make 2 single bonds with lone pair or a double bond with 2 lone pairs like this. This is 0. So do you think I can take this opportunity and make a double bond with nitrogen? Is there any problem with nitrogen? No, nitrogen can have 8, right? So one oxygen is like this. So can I have another double bond with oxygen? No, don't do that. Yes. So now for the other oxygens, you have only one option. Put 3 lone pairs on each oxygen. Complete the octet. Can you tell me how many electrons are here? How many electrons are used? There are 24 total. Are they used? So just count like this 8 because you ensured 8 for oxygen. This will help you doing it faster rather than counting. So is there any lone pair for the central element? Anything left? No. But this is, check the formal charges. Check formal charges. I'm marking them as oxygen 1, oxygen 2, oxygen 3. What's the formal charge on oxygen 1? Oxygen 2, oxygen 3. But there is only one minus. I can see 2 minus. Check nitrogen. Yes, nitrogen is plus 1. Nitrogen is very happy with no formal charge when it is with 3 bonds because it has only 3 unpaired electrons. Check it. Check the configuration of nitrogen. If nitrogen is like this, then it is very happy because if you see the configuration 1s2, 2s2, 2p3, this is the outermost shell. It has 1 paired and 3 unpaired. These 3 electrons can make 3 bonds. How come it is making 4 bonds? Because this lone pair is taken by one of the oxygen. One of the oxygen, see this -1. They are not giving any electrons. So one lone pair is going to make a coordinate covalent bond with the oxygen. Coordinate covalent bond you will not be tested in your AP, but yes, in chemistry Olympiad, yes. It's a coordinate covalent bond. So nitrogen is making a coordinate covalent bond with one of the oxygen. That's why it's getting formal plus. It's giving extra electrons. Ready for another structure? Okay. SF4. Yes, S is the central atom. Then make the skeleton. For the central atom, you can write CN. CA, central atom as I'm asking you to memorize the rules now. Make the skeleton. Do you remember fluorine is never the central atom? Fluorine is never the central atom. Fluorine will never make a double bond, right? Fluorine always makes single bond. So total valence electrons are, Anaya is giving me 34. Is she right, Amodita? If I'm going fast, you can let me know if you feel that I'm slightly faster. Mayank and Amodita, 34 valence electrons. Is it correct? Okay. Complete the octet of most electronegative fluorine with minimum formal charge. Fluorine is not going to make a double bond. It means on the fluorine we have, yes, 3 lone pairs. How many are used? Amodita is telling me 32 are used. How many are left? Where it will go? So sulfur, I'm placing 2 electrons. Let's see if sulfur has any problem. Sulfur has 6 valence electrons. You know that. 6, right? So 1, 2, 3, 4, 5, 6. 6 minus 6, 0. Sulfur is 0 formal charge. It's using 4 in bonding and 2 as a lone pair. So all the 6 electrons are well justified here. So 6 minus 6 is 0. So this is the Lewis-Dot structure of SF4. Remember one thing again, hydrogen and fluorine can never be the central element. So can you draw the Lewis-Dot structure of H2S? Central element, sulfur, skeleton, total valence electrons, complete the octet. I think hydrogen is happy already too. It can make only one bond, no lone pair. Here hydrogen is not the central element because it cannot make more than one bond, and that's why it is out of the position from the center. Now complete the octet of sulfur. What should I do? Sulfur has 4. 1, 2, 3, 4. 2 bonds means 4. Means 4 more needed. This is the Lewis-Dot structure of H2S. Yes. Check the formal charge on sulfur. Check how many it is giving and how many it is using. It is giving 6 valence electrons using 1, 2, 3, 4, 5, 6, 0. What's the formal charge on hydrogen? How many hydrogen is giving? 1. Hydrogen is giving 1. So what's the formal charge on hydrogen here? 0. 0. Right? Okay, so that's the story about your Lewis dot structure. After that, we have to learn VSEPR. Okay, now see here, children. First, you did the Lewis dot structure. We were just doing that only. But that's not the end. You must be thinking that, oh, only this much example. No, you are going to do 100 examples. First, you are going to do Lewis dot structure. After Lewis dot structure, you will decide the VSEPR. If you do error here in Lewis dot structure, you will be doing error in VSEPR. In VSEPR, you are going to decide then electronic geometry. Electronic is how they are arranged in space. You will use 2 words, electronic geometry and molecular geometry. How they are, the shapes, the shape of the molecule. And the thing which we are doing right now is for the covalent molecules, not for ionic compound. Once you have decided these two, then you are going to decide the polarity of the molecule. Polarity of molecule. Molecule is polar, non-polar, like this. Once the polarity of molecule is decided, then you are going to decide the type of intermolecular forces of attraction, IMF. Once this is decided, you can compare the physical properties. Compare the physical properties, boiling point, melting point, freezing, sublimation, and vapor pressure, value of delta H of fusion, vaporization, so many things. This is your unit 3. Starting from here, this is unit 2. You're going to learn all these things in unit 2. And then unit 3. But if you do error here, error, everything will collapse. Okay, so don't do error here. You need plenty of practice for the Lewis dot structure. Without correct Lewis dot structure, you won't be able to predict the correct electronic geometry and the molecular geometry. You won't be able to understand the polarity of the molecule. If you are not able to understand polarity, you won't be able to understand the type of IMF. If you are doing error here, you won't be able to compare their physical properties, which is one big chemistry. Physical properties which are responsible for the change in state of matter, solid to liquid to gas, melting point, boiling point, vaporization, sublimation, fusion, all these words are there. Vapor pressure, high vapor pressure, low vapor pressure, they all depend on physical properties. Big chemistry. Unit 3. So we are ready for VSEPR now. So let's try to understand the meaning. Valence shell electron pair repulsion. Okay, let's make the Lewis dot structure. I'm just trying to make you understand this word. Let's make the Lewis dot structure of CS2. What's the central element? Skeleton, total valence electrons, complete the octet of sulfur. But remember, carbon can make maximum how many bonds? Now you have to focus on carbon also, side by side. Carbon can make how many bonds? Check how many valence electrons carbon has, and all these valence electrons can be excited. Carbon is 1s2, 2s2, 2p2. This is ground state, Amadita. You were not there, so I'm showing you here. Okay, this is ground state. One electron jumps from 2s to 2p so that you have 4 unpaired to complete the octet. So whenever you see carbon, make 4 bonds. Like there are 2 atoms, so 4 bonds will be like this, right? Now complete the octet of this sulfur. You know sulfur in the ground state is? It is neon, 3s2, 3p4. In the ground state, is not using its empty d orbital. So how many bonds sulfur can make? Just like oxygen, it can make 2 bonds. So they can have exactly same number of bonds as oxygen or fluorine, the other elements. It can make 2 bonds, see? And it's making 2 bonds. And you can see the lone pairs. These are the lone pairs. Check the formal charge on every element. Yeah, who is going to tell me the formal charge on every element? Yes, so it's a happy molecule, CS2, no formal charge. Okay, good. Once you have made this Lewis dot structure of CS2, now look at the carbon. This is carbon. So you have to focus on the central element. Around the central element, you are placing an electron cloud. This is an electron cloud. One electron cloud here and one electron cloud here. 2 atoms. Now these electron clouds, they are going to repel each other or they are going to like each other. They are going to repel each other. Now you already know that this is the space around carbon, 3-dimensional space. Now to minimize the repulsion, what nature will do? Will try to put these 2 electron clouds 180 degrees to each other to minimize the repulsion. Nature doesn't like repulsion. You know that nature likes? What nature likes? Attraction or repulsion? Attraction, stability. So when we are doing war, when we are fighting, all these things, nature doesn't want it. Okay, so if you stay cool and calm, then you are going with nature. Going with nature means good health, happiness. Okay, so here to minimize this fighting of these electron pair, to minimize, nature would like to have these electron clouds as far as possible in the space. If there are 2 electron clouds, then this is the only option, 180 degree. You know, this molecule is linear. It's linear with an angle of 180 degree. And if I make it like this, can you tell me, is there any dipoles in the bond? Polarity in the bonds? Who is more electronegative, sulfur or carbon? So this is delta minus and this is delta plus. So draw the dipole. Remember how to draw a dipole? An arrow with a tip in the direction of negative and a tail in the direction of positive. Dipole is a vector quantity. Draw a dipole here. These are, what is a dipole? Dipole is a measure. This is how we measure polarity of a bond. Polarity of bonds based on difference in electronegativity. More difference, more polarity, more charge separation. So can you see that charge separation here? But dipole is a vector quantity also. So what do you think? The magnitude of these dipoles will be same or different? Because atoms are same. But directions opposite. So what happens to the net dipole moment? The sum of these two dipoles. Anaya, why double? Anaya, you are standing here. Here. I asked you to go 2 kilometers to the right side. 2 kilometers. Now you're here. Then I said, okay, Anaya, go 2 kilometers to the left side. Is there any displacement for you? Displacement. Is there any displacement? Zero, because this is +2, this is -2. It's a vector quantity, displacement. But how much distance you traveled, Anaya? Distance. Or you will say, oh, you made me walk 4 kilometers for nothing. Distance is not your vector quantity, it's a scalar quantity. So distance traveled by Ananya is 4 kilometers, but her displacement is 0 because she's back to the original position. Same thing is here. Vector quantities are the quantities which depends on magnitude and direction. Both the things depends on magnitude and direction. So if magnitudes are equal, like atoms are same, polarity is same, but directions are reverse, the sum of all dipoles, which is called as dipole moment, is 0. This is dipole moment. Means the molecule as such, the complete molecule, CS2, this complete molecule as such has no polarity. There's no polarity. And the molecule is non-polar. Non-polar. CS2 is a non-polar molecule. And from there, we'll decide the IMF is non-polar. Then I will be using the word symmetrical. Is the molecule symmetrical? Yes or no? Symmetrical means around the central atom, your other atoms are uniformly distributed in different direction. And then I will be saying, oh, it's a symmetrical molecule. So what's the dipole moment? And you will say if it is symmetrical, 0. And if it is 0, was after you are saying that it's 0 dipole moment, you are going to tell me it's non-polar. Right? Okay, so now I'm giving you one document here. You can have a look in the document every time. Take a printout. There are some errors in writing, just ignore that. I don't have any help and I'm not very good with typing. Typing is something which is causing trouble with me. So if there are some errors, just correct it with your pen. Okay, so take this document. In this document, all the rules for the Lewis dot structures are given. Different types of VSEPR are given. the molecular geometries. In the document, I'm writing it as electron domain geometry, but I'll tell you at that time when we are going to do it. So, are we clear about VSEPR, children? We are clear? Okay. Now, so molecule is nonpolar. Ready for another example? Let's do this one. COS. Central element. Skeleton. Total valence electrons. 16. Complete the octet of oxygen and sulfur. Remember, carbon needs 4 bonds. So when you are looking at like this, so remember the central element at the same time. Oh, I have to take care of carbon also. Carbon needs 4 bonds and complete the octet of oxygen and sulfur with minimum formal charge. So oxygen is very happy in making a double bond with 2 lone pairs. Check the electron configuration. Oxygen has 2 unpaired and 2 lone pairs. So oxygen is very happy like this. Same with sulfur, because sulfur here is not the central element. If it is not the central element, it's going to behave like oxygen, right? So it is also very happy in making a double bond and lone pairs. Now tell me how many electron clouds are here? How can you minimize the repulsion? So look at this electron cloud and talk about electronic geometry, that is 180-degree linear. So the molecule is linear. Is it symmetrical? Mayank, you are wrong. Anaya is right. Can you check why she is saying no? It's not symmetrical. Atoms are not identical. So, no, not symmetrical. If it is not symmetrical, do you think the net dipole moment will be zero? No. The dipole moment is not equal to zero. Mu, the dipole moment. Do you remember the word dipole moment? Amodita, your answers? Yeah. The dipole moment is the sum of all dipoles. So the net dipole moment is not zero. If it is not zero, molecule is polar or non-polar? Molecule is polar. This molecule is polar. Now let's try to understand not symmetrical dipole moment is not equal to zero. Okay, check here. This is oxygen. This is sulfur. Oxygen and sulfur are more electronegative than carbon. We know that, right? So this is how the charge separation will take place. But in which case the difference in electronegativity is more? Which one is more electronegative, oxygen or sulfur? So here the difference is more, so big dipole, big dipole. And on the other side, the difference is less, so small dipole. Let's make it slightly smaller. So if I ask you to do the sum of these two, the net will appear in which direction? The net will appear in this direction. Okay, something is cancelled, right? This much part is cancelled, so the net will be slightly smaller, but it will be in the direction of oxygen. Now, what does it mean? The electron density of the molecule is more in this area. Okay, I'm going to show you in kind of representation to show you that how the electron density will be more in this area. It will be more on the oxygen as compared to sulfur, more on the oxygen, right? So molecule is slightly polar and polarity minus charge is more on the oxygen. There is on the sulfur also, but sulfur is going to have less. Oxygen is going to have slightly more. So the molecule is polar. The sum of all dipoles is not equal to 0 because it is not symmetrical. Ready for another? Make this one without my help and tell me, is this molecule polar or non-polar? And give me the geometry of the molecule. Tell me about the symmetry. So first, give me what is the geometry of the molecule? Electronic geometry of the molecule. Linear, very good. Is it symmetrical? So is it polar? No. Symmetrical molecules are non-polar. So can you see that? And once you will say non-polar, then very soon I'm going to teach you, after making you comfortable with VSEPR, my next target is straight away I'll teach you IMF from chapter 3 because they are connected from unit 3. They are very much connected. When you say non-polar, I'll say, oh, it has weak intermolecular forces of attraction, LDF. You know, CO2 is a gas. CO2 is gas. Why? Because it is non-polar, attractive forces are very weak. So generally non-polar molecules have very weak attractive forces and we call them as London dispersion forces. We have to understand the meaning in chapter unit 3. So right now you can simply keep practicing London dispersion forces. LDF or simply dispersion forces, simply dispersion. There are 2-3 names for it. Right now we can simply take dispersion forces or London dispersion forces. So teachers are more fond of using this LDF. It's easy to write. London dispersion forces. Okay, so we are understanding valence shell electron pair repulsion theory. And we have seen that if there are two atoms around the central atom, so central element X, if there are two atoms, then it's going to be linear, 180 degree. If it is symmetrical, if these atoms are same, you see non-polar molecule because polarity is cancelled out, net dipole moment is 0. So 2-3 examples we have done for this. Now let's go to the second category. In the second category, we have central element surrounded by 3 atoms. What do you think? With 3 atoms, what can be how can you minimize the electron pair repulsion here? How can I minimize 3 electron pairs, 3 electron clouds? Amudita, I can place, what is the total angle here? Total angle? 360 divided by 3. So don't you think yes, I'll place them 120 degree. But for 120 degree, we need the geometry, like here you said linear. 120 degrees like this. Is trigonal planar or trigonal planar. Trigonal planar is completely planar, flat on the paper. Like on the paper, when you draw this line, the molecule is also flat, totally flat. All these atoms, this one, this one, this one, this one, they are lying in the same plane. This is the shape given by nature for 3. Nature said, if you have 3 groups around the central atom, go like this. That's the maximum separation I can give. And whatever nature is giving us, whatever shape nature is giving us, that shape is considered as very symmetrical. Like if I give you something like this, in the center, Then there are 3 atoms on this A, B here, B here, B here. Now all the B's are identical. You can see angle is 120 degree. I'll call this molecule symmetrical. I'll say the dipoles will cancel out completely. The dipole in this direction. This is more electronegative in this direction. So how these dipoles are cancelled out, detailed explanation is not there. For chemistry is not needed. But in mathematics, they are teaching us vector addition, vector subtraction. So these are vector quantities. So the sum of these two will go in this direction. The sum of these two will go in this direction. The sum of these two will go. So they say they cancelled out. They completely cancelled out each other. So trigonal planar is a very, very symmetrical shape if atoms are identical. So ready? So let's do one example here. PF3. Central element, you know, fluorine is never the central element. As it is, fluorine is most electronegative also. Central element, skeleton, total valence electrons. Complete the octet of fluorine. First, check how many used, how many left. Is there any lone pair on boron? Oh, how come 25 Mank? Mank? Getting odd number 25, 27, 31. Then it means electrons are not paired. One electron is unpaired. So your total valence electrons generally is always an even number. In one or two few cases, I'll show you the example where it is an odd number. When it is an odd number, it means that electron is not paired. If Menck is saying 25, it means one electron is not paired. That will make your molecule unstable, right? Okay. So all of you are getting this? How many are used? How many are used? Yeah, are you okay with the structure? So how many groups are there around the central atom? 3. So for the 3, if I make it like this, let's say I make it like this. Do you think this one is better or this one is better? This one is better. Here they are very close. See, even these electron clouds, they are also electron cloud. So they also want to be, if you put like this, then fluorine lone pairs are also far away from each other. Okay, to minimize the repulsion. That's why the name is, sorry, electron pair repulsion. Right? Okay, so it means it is trigonal planar. The electronic geometry is trigonal planar. The molecule is trigonal planar. So is it symmetrical or not symmetrical? Is symmetrical. Polar, non-polar? Polar, non-polar, non-polar. What type of IMF? We'll discuss this later on, but memorize the name. Non-polar molecules, what type of IMF? I gave you the name. LDFs. LDFs. The molecule has LDFs. What is the full form of LDF? Who is going to write? Let's see who is smart. Full form of LDFs. Yes, London dispersion forces. Very good, man. So in non-polar molecules, we have LDFs. LDFs are the weakest because there is hardly any polarity. They are the weakest forces. So till now, what you have understood? If there are two groups, in the groups, I'm going to consider only, right now I'm just teaching you atoms. Very soon I'm going to teach you lone pairs also. If the groups are only two atoms, then it's going to be linear, 180-degree, symmetrical, non-polar, LDFs. But if there are three groups, in the groups I'm just taking only atoms, then it's going to be trigonal, planar. I'm writing TP for it. Angle is 120-degree. If it is symmetrical, it is non-polar, and the attractive forces are LDFs. Now I'm coming for 4. How to arrange 4 groups around the central atom? This is my central atom. Can I arrange like this? Why not like this? Why like this? Because Mayank is already telling me use tetrahedral. Why tetrahedral? Why not like this? Because in tetrahedral, the angle is 109.5 degree. It's a non-planar shape, non-planar. Atoms are not in the same plane. So the atoms are going to be in different planes, making an angle of 109.5 degree with each other. Whereas if I make it like this, it's square planar. Square planar. What's the angle here? In square planar? 90 degree. Now tell me which one is better. Nature is going to prefer 90 or 109? It's going to prefer this one. So when there are 4 groups, then, and if I'm going to take all 4 as atoms, I'm right now just discussing atoms on the central atom, is going to be tetrahedral. Angle is 109.5 degree. You have to memorize it. Right? So ready? We'll draw a Lewis dot structure and then we'll discuss its shape. CCl4. Central element. Remember, chlorine will not make a double bond if it is not the central atom. Just like fluorine. Chlorine, bromine, iodine will not make a double bond. So draw the skeleton. Count the total valence electrons. Complete the octet of the chlorine. Now you can see carbon can make 4 bonds. It's already with 4. 1, 2, 3, 4. All valence electrons used. So no more bonds around carbon. Carbon is done. Now complete the octet. For every chlorine, you need 3. Check how many total valence electrons and how many you have used. How many we have used? Use the same method. This is 8. There are 4 8s, so all 32 are used. Now check how many groups are there, how many electron clouds are there. 4. How nature is going to arrange them? In a tetrahedral. Right now, it appears to you that these are overlapping, but actually not, because they are not in the same plane. One chlorine is pointing towards you. Generally, tetrahedrals, when you are going to do organic chemistry, they are drawn like this. 2 are in the plane of the paper. 1 is pointing out of the paper, out. Other one is pointing away, behind the paper. So this is behind the paper. This is in front of the paper. This is in the paper, so definitely these two will not overlap because they are not in the same plane, right? So this is the best arrangement to have four groups around the central atom with minimum repulsion, tetrahedron. Is it symmetrical? Again, all the shapes given by nature are symmetrical. Tetrahedral is symmetrical. The dipoles will cancel out. Like this is a dipole. This one, this one. If you make a very perfect symmetrical tetrahedral, then the sum of these two cancelled out. The net dipole moment is zero. It's symmetrical. Is it polar or non-polar? The molecule is polar? Non-polar. Non-polar means what type of IMF? LDFs. But chemical bonds are polar or non-polar? Chemical bonds. Chemical bond means the bond of carbon with chlorine. Is that bond polar or non-polar? So there are multiple choice questions. Pick up a molecule which is non-polar with polar chemical bonds. So these type of questions are there. Pick up a molecule from, they will give you few molecules and they will ask you to pick up a molecule which is non-polar, means symmetrical, and but its chemical bonds are polar. So this is one of the examples. There are many such examples. So are we clear about four groups? Tetrahedral. Okay. Now I'm giving you another example. Can you draw? I'm going to give you a mixed example. It can be any one of these, just for practice. Okay, let's work with this first one. Central element, carbon, skeleton. Make the skeleton. Total valence electrons in carbonate. Mayank, 2 minus. 2 minus. Yeah. Carbon can make maximum how many bonds? Oxygen can make maximum how many bonds? So I'm free to make a double bond, right? And complete the octet of oxygen. Do you think other oxygens can make double bonds with carbon? So what you are going to do? Don't make double bonds. Amodita, you're understanding this? Then this, if I don't make double bonds, check the formal charges on each oxygen. Check how many are used. I think all 24 used. 24 is set of 3. This is 3, right? All 24 used. What's the formal charge on this oxygen? -1. This one, -1. You can see 2 minus. These are 2 minus. What's the formal charge on carbon? Good. Carbon is no formal charge. Okay. So now we are going to check the total electron cloud, total groups around the central element in this molecule, in this ion. How many groups? 3. So what should be electronic geometry of the of this ion? For 3, what is it? Trigonal planar. But is it symmetrical? Is this one symmetrical? No, Mayank, no. Can you see this oxygen? They are -1. So whether it's symmetrical or not symmetrical, but it's definitely going to be polar. It's ionic, it's an ion. So whenever you see an ion, we don't discuss symmetrical or not symmetrical. You learn a topic resonance very soon in this unit 2 only. When I teach you resonance, then you will see all the 3 oxygens are identical. Right now you can see, oh, one oxygen is doubly bonded, other 2 oxygens are singly bonded. So that's why she's saying not symmetrical. But no, just leave that and just think of it that this is an ion. So when it is an ion, definitely it is a polar molecule. But otherwise, in resonance, you will see all 3 oxygens will be identical. There is no double bond on any of the oxygen. They will be, all of them are sharing this double bond. So that I'm going to teach you in resonance. Resonance will tell you that, oh, this particular species is very symmetrical. But still it is polar because there is 2 minus ion. So we are good with this. Can we do this one? Central element, skeleton, total valence electrons. Is it 32? No, 26. Yes, 26. Complete the octet of the oxygen. Remember, sulfur can have maximum how many bonds? 6. So you're free to make double bonds on sulfur, right? So can I put a double bond here? Can I put a double bond here? Can I put a double bond here? Oh my God, what we have done? Check here. How many are here? How many total electrons? This is 24, right? But I have 26. Where should I place it? 2 are left. They should go on the central element. But sulfur is already with 6, Mayank. Can you see sulfur is already with 6? 1, 2, 3, 4, 5, 6. It cannot hold these 2 more electrons. So sulfur is already done. Oxygen is done. So this structure is wrong. This is actually of SO3. This is not of SO3 2 minus. This is of SO3. Can you just, okay, let's discuss SO3 then. SO3 has 24 electrons. How many electron clouds are there around SO3? How many? So what should be the shape of the molecule? Shape. Is it symmetrical? So is it polar or non-polar? For the non-polar, you can see NP because I will be asking this question for next, I think 15-20 days. NP. Okay, non-polar. So what kind of IMF is there? LDF. But this is not SO3 2 minus. Now how to make SO3 2 minus? Because this is with 24. So it means I have to remove the double bonds. I have to remove this double bond. This double bond. I need 2 oxygens. There is 2 minus. So I need 2 oxygens which are with single bonds. So I can have only one double bond like this. The other 2 oxygens, they have to be singly bonded to hold this negative charge. This is a hint. If there is a 2 minus, it means 2 oxygens are singly bonded. Now tell me how many I have used. How many electrons I have used? 8, 8, 8, 24. Meg, 24. But how many were there total? 26. So I need one lone pair. Can I put on the sulfur? Yes, I can. Sulfur can take its lone pairs here because sulfur has only used only out of the valence electrons, one sulfur is using here, one it is using here, two here. So out of 6, it has used only 4, so it can hold this lone pair. Now the formal charge on the sulfur is 0. 0 formal charge. But how many groups around sulfur? Oh, this thing we have not done. Yeah, how many groups around sulfur? When you're counting these groups, you're going to count atoms and lone pairs. So by definition, 4 groups are there, but out of 4, 3 are atoms and 1 is lone pair. 3 are atoms and 1 is lone pair. So there are 4. So please write on this. What is the meaning of groups around the central atom? We are discussing everything around central atom. Groups around central atom means atoms on the central atom plus lone pair. So this species has 4 groups. 4 groups means tetrahedral. Let's make it tetrahedral. Tetrahedral is like this. Like this. This is tetrahedral. Make a double bond with one of the oxygen. Make single bond with other 2. Minus here, minus here. Where is the lone pair? This lone pair? Here. It's also on the corner of a tetrahedral. Here. There is no bond. Remove this bond. Bond is there between 2 atoms. But lone pair is exactly on the sulfur. It's in the orbital of sulfur. Can you see this tetrahedral? Is it exactly tetrahedral? Is this molecule exactly tetrahedral? No, because it appears like this. If I show you only chemical bonds, lone pairs are residing in the orbital of sulfur. They are not making bond. Then this is a trigonal pyramidal shape. Trigonal pyramidal. Some teachers, they call it as trigonal. So it's up to you. Trigonal pyramidal. Is it polar or non-polar? So remember I told you whenever there is an ion, then that's going to be polar, ionic, polar. So the lone pairs will distort the geometry. It was supposed to be a perfect tetrahedral, highly symmetrical. But one of the position is occupied by lone pairs, so geometry is now distorted. And this distorted geometry will always going to be unsymmetrical. Whether it is an ion or a neutral molecule, it is going to be unsymmetrical because one position is occupied by lone pairs. Ready for another example of this type? Draw the Lewis dot structure of NF3. Central element, skeleton, fluorine always makes it. These are the simplest one. Within seconds you can make whenever you see fluorine because it's very clear. It's going to make a single bond with 3 lone pairs. Check total valence electrons, check how many are used, how many are left, and where they will go. How many are used in completing the octet of the fluorine? How many are left? They will go on the nitrogen. Nitrogen is still without octet, you can see. Check the formal charge on nitrogen. 1, 2, 3, 4, 5. 0. Everybody is 0. Happy. NF3. Now, how many groups around nitrogen? Groups. For the groups, you are going to count the lone pairs and the atoms. So, what should be the electronic geometry or electron domain? Some teachers, they say electron domain geometry. But nowadays, I have seen that everybody is more into electronic, which is due to lone pairs and bond pairs. No, electron domain geometry or electronic geometry is for 4 groups is tetrahedral. The one Mayank you are telling me, this is one type of geometry, 4 groups, tetrahedral you can see. 4 groups, tetrahedral. But second is because one of the bond is missing. This one is missing. And you are just looking at the geometries due to atoms, which you are going to say trigonal pyramidal here, trigonal pyramidal, and I'm going to call this as the shape of the molecule, shape. This is the real molecular geometry. Molecular geometry, how it is going to appear, the shape in the space. This is molecular geometry. For the electronic geometry, you can use the abbreviation. It's because we are going to do plenty and plenty of questions. That's why I'm giving you all the abbreviations so that you can answer very fast. You can say EG. For the molecular geometry, you can say Mg. If you want to use electron domain geometry, you can say EDG. So electron domain geometry or electronic geometry is decided by the number of groups on the central atom. If it is 3, trigonal planar. If it is 4, tetrahedral. I'm going to teach you 5 and 6 also. But right now my focus is only 2, 3, 4. You're understanding this? Now, when your electron domain geometry is tetrahedral, but the molecular geometry is trigonal pyramidal, they are not same. Why? Because one position is occupied by lone pair. So is it symmetrical? Do you think? No, it's not symmetrical because the lone pairs, they have their own dipole. The dipole exerted by lone pair is different from the dipoles of these fluorine bonds. So the dipole moment is not going to cancel out. So dipole moment is not equal to 0. So this NF3 is a polar molecule or non-polar molecule? NF3. NF3, there is no charge, so you have to say whether it is polar or non-polar. It is polar. It will have a polarity in it. And that polarity is due to dipole. So we call it as dipole-dipole polarity. Dipole of one molecule attracted to dipole of another molecule. So there is dipole-dipole attraction. Dipole is like if this NF3 is, this molecule is there. So there is a dipole like this. There is a delta plus, delta minus like this. The another NF3 molecule, it also has a dipole like this, delta plus, delta minus. Then they are attracted, isn't it? Plus minus attracted to each other. Nitrogen of one molecule attracted to fluorine of other molecule. This is dipole-dipole. We are going to do more in detail right now, just symbolic explanation so that if I say polar, you can say dipole-dipole, right? So this molecule is polar. It has dipole-dipole as well as LDF. LDF is also there. LDF is there in every molecule. LDF, London dispersion, is in every molecule. But here the stronger is dipole-dipole. This example is clear? Okay, let's do one more example. H2O. Draw the Lewis dot structure of H2O. H2O, you know that hydrogen is never the central atom. Hydrogen never makes a double bond. Hydrogen cannot have lone pairs. So H2O is count the groups around oxygen. Make the Lewis dot structure. Are you getting this? H2O. Amodita, are you getting this? Okay. Mayank, done? Mayank and Ananya. Check, are you getting this? Okay, good. Now count the total groups on the oxygen. I'm not going to write anything on the whiteboard. I want to see whether you have understood. 4. Okay. 4 means what kind of electronic geometry, e.g., is tetrahedral? Make it tetrahedral. Like this. Like this. Put 2 lone pairs on 2 corners. So generally, they all are equal to each other, okay? These are equally distant from each other. It doesn't matter. On the paper, it appears that I'm making closer to this one. No. You must be thinking, why she's making here? Why not here? The distance between these two, the angle between these two, how much is the angle between these two? 109.5 degree. How much is the angle between these two? 109.5 degree. So they are at equal distances from each other, right? So here is okay, hydrogen. This is hydrogen. And this is hydrogen. These two are hydrogen. Now, is it a perfect tetrahedral? Now remove these bonds. Bond is not there. Lone pairs are in the orbitals. Like this. In the books, they show like this also. These are orbitals of oxygen. So there is no chemical bond. Now tell me the shape. Shape means the molecular geometry. The way it is appearing. Just ignore the lone pairs. So the way it is appearing is linear. Oh my God. Who said linear? And I also agreed. My God. Is it linear? No. So bent. Bent. For the pyramidal, you need 3. You remember, pyramidal is this. This is pyramid. This is a pyramid with a base of triangle. That's why we call it as trigonal pyramidal. With 2, you cannot make a pyramid. So you're going to learn few more pyramids, like this is trigonal pyramidal. Then I'm going to teach you trigonal bipyramidal. Then square bipyramidal. Square bipyramidal means the base is square like this, and there is a pyramid on the top like this. This is square pyramidal. But if there is another pyramid at the bottom like this, then it is square bipyramidal, which have another name octahedral. So you're going to learn this also. Okay, so this is not a pyramid, it's bent only, right? The structure is bent. And so, do you think it's symmetrical? Is the tetrahedral is symmetrical, but bent, the one which is distorted by lone pair, is not symmetrical. So water is polar or non-polar? Water is polar. So what kind of attractions are there in water? It's polar, right? Dipole, dipole, dipole. Attractions. I'm not talking about the chemical bonds. Anaya, attraction. Dipole, dipole. LDF. But there is one very special kind of attraction, which is just a part of dipole, dipole. It's actually very special dipole, dipole, and we call it as hydrogen bonding. And that you can see whenever you see hydrogen bonded to oxygen, hydrogen bonded to fluorine, and hydrogen bonded to nitrogen, NOF. If you remember, I was telling you these are the most electronegative elements of the periodic table. So whenever hydrogen is bonded to them, there is a big charge separation. Delta En here is very large. So the charge separation is very big. So these are very polar bond, very highly polar bond. The dipoles are very big, special dipoles due to big difference in the electronegativity. Only these three elements, when bonded to hydrogen, can show hydrogen bonds. Water has hydrogen bonds. That's why water is liquid, stronger attraction. So these are the three attractive forces in water. Okay. So we'll continue in the next class from here only. I'll teach again, I'll start from 3 and 4. We have done many examples, then 5 and 6. So in the next class, we'll continue with the VSEPR and whatever we are discussing. We'll make the Lewis dot structure, we'll discuss the VSEPR, we discuss the polarity of the molecules, and it's a very big topic. See you in the next class. If you have any questions, you can stay.